The next topic is forecasting. What we're going to try to do essentially is to forecast the future. And what we're going to do is simply use our past observations, x1 through xn, our corresponding model that we have for them, to forecast, to predict what the next value in the time series would be, x of n plus 1. The one after that, x of n plus 2, and so on. And for time series analysis, this is actually why we're doing it. This is the number one purpose of coming up with a model in time series analysis, is so that you can forecast what future values would be of the time series. So let's consider the case where we want to go m time points into the future. In other words, we want x sub n plus m. And what we will use is the minimum mean square error predictor to forecast it, to estimate it. Notationally, this is given by x of n plus m. And then in the superscript, we put n to represent, hey, I'm using n values from my past to predict this future value. What this x sub n plus m, superscript n, is just simply what I would expect x sub n plus m to be given, so we have a conditional probability here, given all my past values. So this conditional expectation is just like any conditional expectation that you've seen previously in a mathematical statistics course. We work with it exactly the same way. Now, the reason why this is called minimum mean square error predictor is as follows. So in a mathematical statistics course, very typically you'll learn about what's called the mean square error. So it might be represented as something like this. Suppose you have a parameter of interest, just in general, theta, so it's not anything to do with the moving average aspect of a model. This is just in general for any statistics problem. Minus, and let's say we estimate it with theta hat, I square it, and I put a bracket there. This is my mean square error for theta hat. And so notice what this is telling me is that how far is my estimator from what it's trying to estimate? Since I can be on the positive side or the negative side of a theta minus theta hat, let's just square it so that we're always in one direction, we're always positive. And then I want to know, well, how far off on average is theta hat from theta in terms of a squared error? That's a mean square error. And in a mathematical statistics class, often you talk about, well, what kind of estimator is going to result in something that's going to minimize this expected squared error. Because that estimator, that statistic, typically would be the best. And for our particular case here, we're looking for some function of our data, excuse me, such that the mean square error is minimized. And it just so happens it ends up being this expected value, which I think in the end is quite intuitive. What would I expect x of n plus m to be given my past data? Now, in the end, we don't use this exactly. Instead, we're going to use the following estimator. The only notational difference is I'm going to put a tilde here on top of x to differentiate it from what we had previously. And again, it's a conditional expectation. What would I expect x of n plus m to be given now an infinite possible past? So that's what we're going to actually end up using. In the end, the two kinds of estimators will get to the same spot in terms of what the actual values will, what the actual forecasted value will be, in terms of there'll be very, very little difference. And just working with an infinite past is often a little bit easier in terms of our notation. So that's why I'm doing this. Okay. Now also a little other notational thing that I'm going to do is I'm going to let the letter I denote this past. And if I've observed, if I went up to, let's say, n time points, I'm going to denote this as I sub n. So x tilde sub n plus m, and then the superscript n is going to be equal to the expected value of x sub n plus m given I sub n. That's our forecasted value. Excuse me again. Okay, so let's take a look at this relative to our autoregressive 1 model that we've looked at a lot already in this course. So here's what our model looks like. X of t is equal to phi 1 times x of t minus 1 plus wt. The wt's are independent with a mean 0, variance sigma squared w. If we were to do estimation, again, we would typically put a normal distribution with that. Now, our observed data is x1 through xn. And notice because of how this model is constructed then, essentially this also means w1 through wn is observed too. This will be important as we move along. Okay, let's say that again I want to go m time points into the future. So I want to get at x sub n plus m. Well, in terms of our model, this is what it will look like. Wherever you see a t, you put an n plus m. And let's now look at just one time period into the future to see what that forecasted value would be. So m is going to be equal to 1. So in terms of our notation, this is what the forecast looks like. In other words, just the expected value of x sub n plus 1 given I sub n. So in case I didn't say this, I stands for information. That's why I chose that letter. Then I put in, well, what does my model look like if I have m equal 1 in it? So its expected value is phi 1 times x sub n plus w sub n plus 1 given I sub n. Then next, I bring my expectation through the sum. So now I have two separate expected values. And let's take a look at this far right expected value there. Okay. We have not observed anything about the n plus 1 time point. This is one time point into the future. And so all we know is that this w is independent of other w's with a mean of 0 and a variance of sigma squared w. So when I take then the expected value of this x of n plus 1, and I know it's independent of this past, well, that expected value then is simply 0 because of this right there. This other expected value, I can factor out the corresponding constant, that phi 1. So I'm going to factor that out there. And then I'm looking at, well, what would I expect x of n to be on average given this information from my past? Well, in that past, x sub n actually exists. So it's like saying, okay, what's the expected value of a random variable given I know what that random variable already was observed to be? Well, it's then that numerical value of that random variable. So this expected value is just simply x of n. And so my first forecasted value, meaning one time point into the future, is simply phi 1 times x of n. Let's look at m equal 2. So now I'm going 2 time points into the future. So I need to find the expected value of n sub plus 2 given my information up to time n. So that's, let's say, step 1. Step 2 here, I plug in what the model would be when m is equal to 2. Step 3 then, I move the expectation through the sum. Step 4, this expected value for w sub n plus 2, again, is equal to 0. Also, I can bring this constant, phi 1, out in front. And I'm left with the expected value of x of n plus 1, given this past information. Well, this is exactly what we just found above. So I could write this as phi1 times x tilde sub n plus 1, and then in the superscript in n. Now, if one wanted to, one could put in, well, what was that value? Well, remember, this was phi1 times x of n. So look what ends up happening. Then 2 time points into the future, my forecasted value is phi1 squared times x of n. And you can keep on going, and you're going to see that same pattern that occurs. So again, this is phi1 squared times xn. This is going to be phi1 cubed times the xn, and so on. And so that's what you end up getting. Now notice what's going to happen here. Remember, this phi1 is going to be between -1 and 1. And so when I'm squaring that number, when I'm cubing that number, when I'm taking a fourth, taking it to the fourth power, and so on, this leading number in front of x of n is going to get smaller and smaller and smaller in terms of its, I should say, instead, it's getting closer and closer to 0. And so for this kind of a model, where originally we assumed that the expected value of x of n was equal to 0, this is again the standard that we've been working with, this forecasted value is going to go to 0. Okay. Now, of course, in real life, we're not going to know what the fees are. So what you're going to need to do for the forecasted value is simply replace the fees, or replace phi1 with its corresponding estimate. That's going to be our forecasted value. This is the notation that we're going to use for it. Now, this is somewhat of an abuse of notation. Don't blame me. This is standard amongst time series textbooks. I just decided to keep this standard. You know, what would have been better to do is that once I put a hat on top of the phi, I also put a hat on top of the tilde, which is already on top of the x. So most textbooks don't like to keep on adding different marks to the notation, and so I'm not going to go ahead and do that. It should be clear based upon the application. You know, do we want the true forecasted value, or do we want the estimated one? Okay, so a question here. Well, what happens to the forecast as m goes to infinity? We've just talked about that. We're going to 0. But if mu was not equal to 0, though, this is what our model will look like. And notice we would have this always this constant out in front. So instead, what's going to happen to these forecasted values, instead of going to 0, it's going to go to mu times 1 minus phi1 as m increases. Okay. Well, so that was an AR1. Let's take a look at a moving average 1 model. Again, I'm interested in, let's say, m time points into the future. This is what the MA1 model course looks like. And if I were to write everything in terms of m time points into the future, I replace the t with n plus m. And so if we let m equal 1, let's look at what happens. Excuse me. So my first forecasted value, x tilde sub n plus 1, based upon information up to time n, is again just simply the expected value of x sub n plus 1 given my past information. I then put in my model where everywhere I had a t before, I'm going to put an n plus 1. Then I can move my expectation through the sum. I can factor out constants that are inside the remaining expectations as well. And we've already seen this right here. What's the expected value of w sub n plus 1 given my pass? Well, that's equal to 0. And what's the expected value of w sub n given information up to time point n? Well, as I said before, given our model structure, and given that we've had information up to time point n, essentially we've observed w1 through wn. And so what is this expected value of Wn given I sub n? Well, just Wn. So the first forecasted value is theta 1 times Wn. More about that W shortly. If I go 2 time points into the future, now I'm looking for the expected value of n plus 2 given my past up to time point n. I write what my model is for x of n plus 2. I distribute the expectation through, factor out constants. This expected value of w sub n plus 2 given my past up to time point n, that expected value is 0. Also, the expected value of w sub n plus 1 given information up to time point n, we've seen this before, that value is 0. So theta 1 times 0 is 0, plus 0 is 0. And I quickly have my forecast become 0. And the same thing is going to happen for 3 time points into the future, 4, 5, and so on. So you can see the difference between that moving average model and the autoregressive model. The autoregressive slowly goes to 0, or whatever constant you have there, if mu does not equal 0. For the moving average model, we quickly go to 0, corresponding to what the value of Q is. Now, of course, with this kind of model too, I could also have the expected value of x of t be equal to mu, where mu is not equal to 0. And in that particular case, for a moving average model, the forecasted value will quickly go to whatever that value of mu is, just like what we saw for 0. Okay, so what do we do about this Wn? So again, x of n plus 1, superscript n, again, maybe I should have mentioned this before, with that superscript there, that does not mean I'm taking it to a particular power. So I'm not like squaring it or cubing it. It is just a symbol that's frequently kind of used in statistics when you already have something in the subscript and you still need to denote some other information. Well, let's put it in the superscript. I mean, sometimes there's even notation in statistics where you will see somebody will do it with like a pre-subscript or a pre-superscript. They will actually put stuff up there too. Fortunately, in our course, we won't need to go to that extreme. Okay, so again, the n in the superscript means I have information up to time point n. Now, for this particular model then, this is what that first forecasted value would be. Well, what exactly is that Wn? Okay. Now, this forecasted value, what I'm going to actually calculate when I estimate it, of course, I'm going to put a hat on top of that theta 1. So I can get it from my model. And also, I'm going to put a tilde on top of my W in a superscript n here as well. Because, as I said, we essentially observe the W's. We don't exactly, but we essentially do. And so it's going to take a little work to get what we would have for Wn. And it's sort of like an estimate for what that Wn would be. And, well, what is that value? Well, it comes directly from the residuals. You know, think back to what a regression model would give you for your residuals there. How you can kind of think of that as a way to estimate what the epsilons would be, that random error term that you typically have with a regular old regression model. Okay, so how do we find these residuals? So at time point t, W tilde with a superscript n is going to be how we're going to denote the residuals. And to see how to get the residuals, just rewrite our model. So normally we write our model with x of t on the left side. How about we rewrite the model with now Wt on the right side? So all I did was some algebra with our original model that we have here. So in other words, I just brought this over there and I changed the sides for the W sub t. Okay, well, based upon this representation of our model, then W1 is equal to, well, x1 minus theta 1 times W0. Of course, we never observe time point 0. So what should we do there? Well, remember that the mean for white noise is 0. So how about we just put 0 in there? That would be one way to handle it. And that's the way we're going to focus on here. So this first residual then is just what x1 is. Then for time point 2, I take x2 minus theta 1 times, well, what I have for W1. How are we going to find that W1? Well, let's just put in what that first residual is. So in other words, that's going to be x1 right there. And we can keep on going and iterating through this process until you get to Wn. And W sub n tilde with a superscript n then is x of n minus theta hat 1 times that previous residual. So you can see it can take some work to actually find these kinds of residuals. More complicated models follow this same process. If you want to see another example of this, Shumway and Stouffer's book have an example dealing with an ARIMA 1.1 model. We will simply, rather than going through this by hand, we will simply focus on getting the residuals that are automatically found for us in R, rather than going through all this step by step by hand. So as you will see shortly, R automatically does these calculations for us. Now do note though, there are alternate ways to find these residuals. I've essentially shown you what the easiest is. Another way is, so for example, we had that problem with what W0 is. What one could do is actually do what's called backcasting, which is, you could say, the opposite of forecasting, where now you're trying to get at what these past values would have been if we would have actually been able to observe them. That will then allow you to take care of that W0 issue, and you could replace that W0 with an estimate. I don't think it's really worthwhile for us to spend time going through those kinds of details. Okay, so let's take a look at one of these more complicated models, an ARIMA 1.1.1. Okay, let's see here. So again, let's say that I want to know what the forecasted value is for m time points into the future. Here's what our model looks like for an ARIMA 1.1.1. If we did a little bit of algebra, we could rewrite the model so that only x of t is on the left side. Make sure excuse me, you can do that just for practice. So that at time point n plus m, this is what we're after. So x of n plus m represents, you could say, the true value that would be observed in the future if we went actually m time points into the future. Since we only have information up to time point n, we're going to try to estimate it with x tilde sub n plus m and then superscript n there. Okay, so let's look at what happens when m is equal to 1. So I'm going to, everywhere I have an m, I'm going to put in a 1. So x of n plus 1 given my past is equal to the expected value of what we have above there, but now again with m equal to 1. So let's say that's step 1, this is step 2. Step 3 of this process, then we move the expectation through. We factor out constants from each of the expectations, and this is what we get. Step 4, we find what these expected values are. So the expected value of w sub n plus 1 given my pass up to time point n, of course, is 0. So that's where we get that from. I have an expected value of w sub n given my pass up to time point n. So that's why I have an n there, w sub n there. What is expected value of x sub n minus 1 given my pass up to time point n? Well, I've observed what that x sub n minus 1 is, so I'm going to put x sub n minus 1 there. And a similar thing which we've seen before for expected value of x sub n given I sub n. Okay, so step 5, I just do a little bit of simplification. And so this is what that forecasted value would be. So at 2 time points into the future, I can go through that same process. I'll let you go through the details on your own. Do note that now these W's disappear because now my W's have indices that are greater than n. Okay, so in summary, this is what we get then for these forecasts. Once again, the parameters will be actually unknown in actual application, so we'll get our estimated model, and we'll put hats on top of all the parameters. Also, we will replace the W sub n's, or replace the W sub n with the W tilde sub n with the superscript n as well. Okay, so let's take a look at an example. This goes back to our AR1 example that we've seen previously. Now we're going to use data with it. While the data was simulated, assuming that mu is equal to 0, in actual application, we would not know that mu is equal to 0. So it's best to approach this by actually estimating that constant term that's in our model. And so here we go. So I read in my data as we've seen before. I estimate the model as we've seen before as well. Here's phi hat 1. Here is mu hat as well. And here is sigma hat squared W. We've seen this all before. Okay, now let's do some forecasting. The function in R that's used to do the forecasting is called the predict function. You've likely seen the use of a predict function before. So like, for example, with regular old regression analysis to come up with your y hats and the corresponding confidence intervals for the expected value of y, one uses the predict function for it. So the predict function in R is actually a generic function. And so now when we use predict with our results from the ARIMA function, remember the class of mod.fit is ARIMA with a capital A. And so the actual function that R is going to implement here is predict.ARIMA. Here are the corresponding arguments. My object that actually stores the information from estimating the model was called mod.fit. And let's say that I'm interested in going ahead 5 time points in terms of my forecast. Now, what this actually means in R's terminology is that you want time point 1, 2, 3, 4, and 5. So you're not just interested in time point 5. You're actually interested in time point 1 through 5. And that should generally make sense. One generally does not, let's say, start looking 5 time points into the future. You want to see what the first time point into the future is, the second, and so on. So n dot ahead equal 5. So I'm going to get 5 different forecasts. So I'm going from n plus 1 to n plus 5. se.fit equal true. This corresponds to that what I want is the estimated variance of what's called the forecast error. So it's going to be this. Actually, it's going to give me the square root. Let me just quickly write it out. So x of n plus m minus that forecasted value that you could say is my forecast error. How far am I off? And I want to know what the estimated variance of that is. And if I take the square root, then I'm finding the standard deviation. This is what se.fit corresponds to. Later in the notes, we'll talk about what the actual mathematical expression for this variance is. We won't talk about it right now. I just include it here because whenever we do forecasting, we will always want to calculate it. Okay, so I'm going to store my results from the forecasting into an object called for.mod. And it returns a list that has 2 components, the forecasted values and these standard errors. So, and also it returns it in a TS class format that we've seen previously too. So this first value that we see here, this represents x sub 101 because we have 100 observations in our data set, tilde, and then in the superscript 100. In other words, it's xn plus 1 n tilde. Okay? This value right here is x105 100 tilde. Okay. So in other words, well, yeah. So yeah, never mind. Here's the corresponding estimated model that we've found before and we've stated before. Notice that this is the constant term that we need to worry about. And one could rewrite the model so that only x of t is on the left side. And this is very helpful in this situation when we're dealing with forecasts. So, what is my first forecast value? If I were to find this by hand, and you may need to find this by hand on a test to show me that you can do this. So we're not only going to rely on R to do these kinds of calculations. And the reason being is because forecasting is so important. And relatively speaking, once you understand how to work with expectations or these conditional expectations, it's fairly easy to find what these forecast values should be. Okay, so based upon what we've had previously for an AR1 model, here's now my constant plus phi hat 1 times x sub 100. This is my one time point into the future forecasted value. So based upon what we have above, here's my constant, negative 0.1360, plus phi hat 1 of 0.6854, times then what x sub 100 would it's actually observed to be, 2.0371. So if you go through the math, you get 1.2602. And guess what? That matches what R actually produced for us from the predict function. So now if I go 2 time points into the future, you can go through the mathematical steps on your own. Notice how 1.2602 now drops down to that, so that we can use it for that second forecast value. I get 0.7277, which is what we had from R as well. Okay. So I've also went through the process for 3 time points into the future, and it matches what R gave us as well. Okay. So now let's look at some plots. I think these kinds of plots are kind of one of the fun things to do in time series analysis, so you can see how your model is working relative to what was observed, and so that you can better picture what is going to happen in the future. So my results from the ARIMA function are stored in mod.fit. And if I say names of mod.fit, I get information about what's inside this list. And one of the items inside that list is called residuals. And so if I pull residuals out of mod.fit, I get a TS class object. And this is what I get. So for example, this 2.624 is W tilde. Let's see, that would be 100, my last residual. And so if I wanted to, I could actually, in this particular case, because it's only an AR model and I don't have past residuals to worry about to find the current residual, what I could do then, let me just bring my model back here. Copy and paste it. Just a second here. Okay, whoops. I can rewrite my model so that I have WT just on one side of it. And let's say at time point, oops. Let's say I want W sub 100. So wherever you see a T, I'm going to replace it with 100. And so here is X sub 100 corresponding to that. Next, here's my constant right there. So I'm just pulling this information out of mod.fit. Notice here's X99. That would go right there. Here's my phi hat. Sorry, this is getting a little bit messy. And then this would give me then what W tilde sub 100, what the superscript 100 would be. And let me erase this now so that we can see what the value is. The value is 2.624, which matches what R actually gave us. Now, this calculation here was pretty simple, and the key is because notice I only had one WT here, so I didn't have to go through the process like what we saw with the moving average model of iterating through all the past residuals. Let me go ahead and delete that. So now that I have these residuals, what I would like to do is now do a plot of my observed data, like what we've done before, plot of the time series. But also add my corresponding forecasts. We'll go up to m equal 5, so 5 time points into the future. And then also for visual display, this is sometimes added, and I'm going to do it right here, is also include my corresponding predicted values for t equal 1 through n. Now we really haven't talked about that exactly, how to find this out, but here's a simple computation that allows you to figure it out. We just calculate essentially a residual. Now, back when you first learned about a regular old regression model, you learned that a residual was equal to your observed value minus the predicted value. In other words, you probably use y as your dependent variable or your response variable. You would take y minus y hat. Well, notice what I could do is bring this predicted value over to the left side, bring my residual over to the right side. So now, if I somehow knew my residual beforehand, I can come up with what that predicted value is. And so I'm going to use that trick here, essentially to find what the predicted values would be for x of t for t equal 1 to 100. So I take my x, I subtract off my residual, and here is the predicted values. So this is the predicted value for x100. Okay. So now that I have these predicted values, let's now do that plot that I've been leading up to. So here's my regular kind of code that we've seen before to do a plot of a time series. So I'm plotting my time series right here. The one difference is that I'm going to specify what my x-axis limits are, because by default R would only go up to time point 100 because that's what's in x. But since I also want to show what the forecasts are, I will extend my x-axis out to time point 105. Then, to get my forecasts and also these predicted values for t equal 1 to 100 on my plot, I'm going to use simply the lines function, where just like what I did previously, I find these predicted values for t equal 1 to 100. Now I'm going to combine those together with those forecasted values for time point 101 to 105. So I simply pull those out of for.mod where we had saved them from the predict function. I'm going to use a type equal O way of plotting this, so I'm going to get a line and points out at the same time using a plotting character number 17. Then I'm going to put a legend on my plot so that everything's nicely identified, and here's the corresponding plot. And so remember, we observe information up to time point 100, so what we see is here are these forecasts. So you can go back in the notes and see, for example, might as well do this, what was that first forecasted value? The first value was, just a second here, 1.2602. And let's just confirm that that place is on the plot. So right there, that's 1.26 relative to the y-axis. And as we've seen before, because we're multiplying these each of the forecasts by phi hat 1, essentially these forecasts are going down to what the constant is for our corresponding model. And that's where they will end up being if you made m very, very large. Now also what we see in this plot here is what I've labeled in black are these predicted values for time point 1 to 100, and then also I just put the forecast in black as well. In red is the actual observed time series. And so we can see how these predictions are following what the observed values are. in some places, it looks like almost like, these predictions are maybe one time period behind in actually getting at that forecasted value. And to some respect, this is due to, this AR1 model in terms of what we see as the autocorrelation between successive time points. We have a positive, relatively large autocorrelation because of what ended up with our model for what phi hat 1 is. And so it kind of makes sense that, as you're, let's say, going up in your time series, that forecast value is going to keep on falling. And if for some reason now your actual observed time series drops down, well, the model says I have a positive autocorrelation. So the model is going to probably keep on going back up. And then eventually, once it sees it going down, it's also going to fall down without going into all the details. So this is not necessarily unusual what we see here. Now also what I can do is I can zoom in on the plot, because typically in most applications what we're really concerned about is these forecasts and maybe how did the model do for a few of the time periods up until we actually do the forecasting, meaning for time point n+1 and on. And so to zoom in here on this plot, what I'm going to do is fix my x-axis to be between 96 and 105. Again, we've observed 100 different time points. And so now we can see, maybe a little bit better how the observed and the forecasts are working together. And and so there we go. There's the plot. Again, we see these forecasts are going down to what that constant value would be. Let's look at a second example in R. This deals now with the ARIMA 111 model that we've seen previously. Just as a reminder, here's what phi 1, theta 1, sigma hat square was. And in this particular case, note that we have a sample size of 200. So I read in my data like I've done before. I estimate my model as I have before. Here's phi hat 1. Here is theta hat 1. And here is sigma hat squared W. This leads then to our stated estimated model as seen here. We can rewrite this estimated model so that only x of t is on the left-hand side of it. So to find my forecast for, let's say, 5 time points into the future, I can use the predict function once again. I store my results for my model fit in an object called mod.fit. N.ahead specifies I want time points 1 through 5, and se.fit means yes, I do want the standard errors. I put the results into for.mod, and here we go. So this first value listed here is x tilde sub 201, given information up to time point 200. Here we have x tilde 205, given information up to time point 200. For some of our calculations that we're going to need, we will need what x sub 199 was and x sub 200 was as well. And here's then the corresponding residuals. So here's w tilde. This would be 200, 200. Okay. So based upon our derivations before for an ARIMA 111 model, here's how the actual forecast would be found by hand, let's say, for time point 201. So I take 1 plus phi hat 1 times x of 200, which we just found above, negative 488.4823, right there, minus, here's phi hat 1 again, times x sub 199, right there, plus then a theta hat 1, 0.4681, and then times that last residual, 4.908614. If you go through the math, you get negative 486.36. Now, just for emphasis, on a test, I might actually have you go through these by hand calculations like this to show me that indeed you understand how these forecasted values do come about. So we can go now to 2 time points into the future. Go through the calculations on your own. Notice you get negative 484.93. Notice also how that that residual no longer is at least stated in there. Obviously, though, it does have a part in that x tilde sub 201 superscript 200 calculation. 3 time points into the future. Notice I have now both of the forecasted values in there from the previous 2. And again, just applying what we had done, what we had written out previously. So let's take a look at a plot of the forecast as well. So I use my standard plotting methods here. So I plot my data. I use the lines function to get both my predicted values from t equal 1 to 200 and the 5 forecasted values. Use the lines function to get that on my plot. And then I use a legend to allow me to identify what each line represents. And this is what we get. Since we have 200 values, of course, it's harder to see everything that's on the plot. So this is definitely one of those situations where zooming in on the plot is very helpful. So I zoomed in on the last the last 10 points that are essentially plotted. And this is what we get. So we can see from the observed, that's the red line there, the predicted for time points 196 to 200 in black, and we can see how everything's kind of following the same trend. And then here are the corresponding forecasted values into the future. Okay, so then that concludes then how we can find then these forecasts for future values of a time series. Once again, let me just emphasize, this is usually the main point of time series analysis, is to do these forecasts. And so this is one of the most important things then that we will talk about in this course.